Shooters, reloaders, and conversationalists, welcome to PounderLabs. Rimfire Redux, powder burning rates, welcome to the deep end of the pool for a 22 long rifle. Sectional density is more important than most shooters realize. It's used in terminal ballistics by hunters to select the appropriate round for game they're interested in. We're focused on internal and external ballistics. All bullets, regardless of shape, for a given weight and diameter have the same sectional density. These two bullets for 38 Special, from a sectional density point of view, the only thing that makes them different is their weight. Sectional density is easy to calculate. Weight of the bullet, measure the diameter to calculate cross-sectional area, and we have it. Most shooters are familiar with ballistic coefficient. Let's see how this ties in. Again, having sectional density, the only other thing we need is a coefficient of form, which is based on the G models. For instance, here's the one for G1. So once you have those, ballistic coefficients, nothing more than the sectional density divided by this coefficient of form. Let's take an example, 30 caliber bullet, 168 grain, like what you would use for a .308 Winchester or 30-06. The sectional density is the weight of the bullet divided by 7,000 to convert from grains to pounds, divided by the diameter squared, and here's our sectional density. Now that we're going to look at the type of bullet, to get this coefficient of form, we have to understand more. In this case, for a boat tail hollow point, sectional density over ballistic coefficient, and then there's the number for the coefficient of form. In his paper, Relative Burn Rates of Powders, Roberto Serino put forth the idea of powder sectional density. It's possible this idea has been around for some time, but this is the first time we saw it expressed in about 2007. We strongly encourage folks to read the paper and understand the working assumptions that are made. Powder sectional density parallels sectional density for bullets. Here we're going to take the charge weight in grains and use the cross-sectional area of the bullet. So powder sectional density, simply the charge weight divided by the cross-sectional area. Let's take an example from his paper, 52.5 grains of 4350 for 30-06, 220 grain jacketed bullet. The powder sectional density, 52.5 over the diameter squared, and now we have the powder sectional density. This is a fairly new idea to a lot of folks, but kind of think about it this way. We have a bullet which has a mass, weight, a diameter, being pushed down the bore by another plug of powder of mass of diameter. And so you think about it in this way, you can see some simplifying assumptions which will be very useful for us to do some basic modeling. Now we move on to relative burning rate, RBR for short. In the previous slide, we have powder sectional density. The only other thing we need now is muzzle velocity. The relative burn rate is approximately equal to muzzle velocity over the powder sectional density. Let's take the example from Serino's paper. We're down to this point. We had the muzzle velocity, and we're easily able to calculate the relative burn rate. He goes on to give some other measures. So relative quickness is the relative burn rate times 100 divided by the gravitational constant, and we get 13.6. Further, the DuPont index is relative quickness times 7 for 7,000 grains per pound, and we get 95.3. It's important to remember some key things. This is for smokeless powder, and it's very application specific. We'll touch on that again in just a moment. And these are for relative rankings, and at this point we don't have any information entered into the model concerning breach pressures, which can be very important. Now let's move on to relative burn rates for our rimfire projects. We use the powder sectional density just the way it's been described previously. The speed of sound is almost entirely dependent on temperature, so it can range from 1100 on a cold day up to more than 1160 on a hot day, which is a 50 feet per second difference. This is easy to do by computing the Mach number, which is the muzzle velocity over the speed of sound. Our proposal for the relative burn rate for rimfire is the Mach number over the powder sectional density, and we scale it by 1,000 just for convenience. Let's take an example. Here's 1.09 grains of powder in the Ely standard round, and here's our bullet, the standard 22 rimfire diameter and weight, and we calculate our powder sectional density here at 21.7. The speed of sound when we did this test is here, and here's our muzzle velocity. So we easily correct with the Mach number. So the relative burn rate for rimfire, 1,000 times 0.96 over 21.72, and we get 44.2. We want to mention we're going to drop units because we're only interested in relative rankings and making it more convenient to visualize comparisons. In this table, we have test results and some comparisons. Let's start at the bottom. This is the 30-06 example with 4350 from Serino's paper, and there's our calculated value for burn rate. Moving up, here's 6.5 Creedmoor, shot with Savage bolt gun with rotor 15, and it's a little quicker. Here's a 300 Blackout, again shot with bolt gun with H110, and it's quicker than that. These are all pistols, but let's take a look. Both of these are 38 Super, shot out of a Kimber 1911, Unique and Bullseye. And we can see that Unique is a little slower than Bullseye. This is a Smith & Wesson Model 52, which is a 38 with Bullseye. And you'll see a difference here between Bullseye for these different two guns. This is a point we were making earlier. It's important to keep in mind what kind of firearm, what type of primer, what kind of load you're working with, because these measures are relative. If we move up, these are just two reference values, but the reason we chose them for 9mm is both Clay's and H310 are probably a couple of the quickest powders that are retail available, and you can see what the index is. All of these were shot with the CZ457 24-inch barrel. Normally for match grade rimfire they use a 26-inch barrel, but we're just having to make do with what we've got. So we start at the bottom here with the CCI Veloster, and then move up into some of the Remingtons, T-Bolt and Target. Here's CCI Blazer, 3 different European blends, and now up we're here at some Federal 714 and 711B. So we think that Serino's method looks like it makes sense. And even though these comparisons are very different firearm configurations we have here, we're kind of surprised and pleased by the tie-in. What you'll notice is that all the 22 long rifles quicker than even the most the quickest available retail suppliers right in through here. So all of these are custom blends supplied on an OEM basis. A couple of comments on the powder morphologies. It's kind of qualitative. The Federal is a shiny, flaky powder. You see them sitting up here at the quickest. What was interesting is all of the European ones were a greenish gray, and there's fine spherical. So you find that this is from Germany, this is from England, and this is older from Yugoslavia. But you'll see they're all very comparable, and the powder on all 3 of these is the same kind of look to it. On the Remington, we see down here it's kind of a dull black and not really sticky flattened spheres. And for the CCIs here and here, one was more of a shiny black and sticky, and the other one is shiny black and semi-sticky. We realize that's kind of qualitative, but you can start to see some interesting comparisons when you start putting all this into the mix and taking a look at it. Here's our test data plotted graphically. Relative burn rate increasing in this direction against muzzle velocity and Mach number in this direction. And this is the linear regression. Given the challenges of making these measurements, we have a pretty good fit. The way a manufacturer is generally going to use this, they're going to design a region that they're interested in, choose a powder, and then do a ladder development over a velocity range to dial that in. A couple of comments. Our measurements are based on powder weight, but one should consider what this means from the standpoint of low densities, and also begin to bump this against chamber pressure profiles. As interesting as all this is, it's not a substitute for testing on the range. And this is because we want to understand rimfire relative to the speed of sound. Regardless of what's printed on the box and the marketing information, we have subsonic down here and supersonic up here. But for rimfire, it's also important to understand this transonic region. The reference value used in aeronautics is about 0.8 to 1.2 Mach. Well, if that was the case, everything we shoot in rimfire from 0.8 down here to 1.2 would be transonic. And we know from actual practice it doesn't work that way. So we think the transonic, or the critical part of that region, is someplace right in here. But you need to do a lot of testing to make sure you understand what the performance is by measuring hits on targets. For folks interested in a lot more detail on that topic, I recommend you go to a YouTube video here on using Schlieren photography to watch what happens to bullets in different velocity zones. We use this by determining relative performance between suppliers. We also are interested in lot-to-lot performance variances, and then on to different types of R&D projects. Stay tuned for new projects as we continue on with our Rimfire Redux projects. This completes our presentation, and as you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your protection and ours. Thanks for watching. Be safe. See you soon.